Hello and welcome to All Maths Considered. In this video, we want to start investigating the concepts of basis change on a concrete example of plane reflections. So our task will be to find the matrix of the plane reflection, which we call phi, with respect to the line L spanned by the vector V. Let's say we'll take the vector 3, 2. So in the picture, here's our coordinates. Here's a vector with coordinates 3, 2. That's a vector V, and that's a line spanned by this vector. And we are looking at the reflection phi with respect to that line. In other words, we want to find the 2 by 2 matrix A such that for any vector V, the reflection of that vector V is equal to AV. So A is a matrix corresponding to the reflection. The reflection is given by multiplication of the vector by this matrix. We shall do that by using the concept of change of basis. And we start by the following important observation. We do know what this reflection does to some specific vectors. For example, we do know that if we take vector V itself, 3, 2, then the reflection will preserve this vector. It will map 3, 2 to 3, 2. The other vector for which we can easily see what the reflection does is the vector orthogonal to this vector. So any vector orthogonal to this vector. From the previous video about rotations in the plane, see the link above, we have several ways to find a orthogonal vector. So in particular, if we want to rotate counterclockwise, all we have to do is to swap the coordinates and change the sign of the first one. -2, 3. In the picture here, that would be this vector. -2, 3. That's orthogonal to the line L. Clearly, the reflection will just map this vector to minus itself, to -3. Okay, so let us call this vector u1 and this vector u2. And notice that u1 and u2 form a basis. They form a basis because they are not lying on the same line, so they are linearly independent, and of course any two linearly independent vectors in the plane will form a basis. And what we have just noticed is that phi takes u1 to u1 and takes u2 to -u2. We shall now break our derivation in the following 3 steps. So step 1, we will write our vector v, which we want to reflect, as a linear combination of vectors u1 and u2. We need to find the coordinates alpha and beta. So notice that alpha and beta are coordinates of v in the new basis u1, u2. Step 2. In the new coordinates, we do know what the matrix is. So in the new coordinates, with respect to the new basis u1, u2, we do know what the reflection does. It simply takes alpha beta to alpha minus beta, because we know what it does to the basis vectors. It fixes the first basis vector and maps the second basis vector to minus itself. So the matrix, so its matrix in the new coordinates is very simple. It is simply the diagonal matrix 1, 0, 0, minus 1. And as a last step, we need to interpret this in our coordinates with respect to the old basis. So as a last step, we will note that reflection of V is equal to alpha u1 minus beta u2. This is because of the linearity. If V is alpha u1 plus beta u2, then phi of V is alpha u1 minus beta u2, because we change the sign of the second vector. And express this as phi of V is equal to AV. So let us now proceed going through the 3 steps with our specific example. So step 1. For vector V, we want to find its coordinates alpha and beta with respect to vectors 3, 2, this is u1, and u2, this is minus 2, 3. Now comes an important step. We can reinterpret this equation here as a matrix multiplication. Here is the way we write it. I take the matrix 3, 2, minus 2, 3, and multiply it by the column matrix alpha beta. Remember that one way the matrix multiplication can be interpreted is that when we multiply the matrix by a column vector, it is the same as the linear combination taking the first column times the first coordinate and the second column times the second coordinate. That's exactly what's written here. Note that in the first column here we have u1, and in the second column here we have u2. Let us call this matrix P. So P is formed, this is a 2 by 2 matrix, by taking u1 and u2 as columns. So we're taking the new bases and putting them as columns to form a matrix. This as a vector equation will simply say then that V is equal to P times the vector alpha beta, or if we rewrite this, we can find the coordinates alpha beta by multiplying by P inverse. Multiplying, be careful, from the left, so we have this equal to P minus 1 times V. P minus 1 is the inverse of this matrix. Step 2. In the new coordinates, phi simply takes alpha beta to alpha minus beta. So its matrix in the new coordinates is simply 1, 0, 0, minus 1. Right? So combining this with the previous step, we see that the vector alpha minus beta is this matrix 1, 0, 0, minus 1 times alpha beta, which of course is just 1, 0, 0, minus 1, and alpha beta was P minus 1 V. Okay, on to step 3. We can now write our reflection phi of V as alpha times 3, 2 minus beta times minus 2, 3. That we know by linearity. Again, using the same trick as in step 1, we can rewrite this as a matrix equation. We have the same matrix P, 3, 2 minus 2, 3, which we now multiply by alpha minus beta. P times alpha minus beta. Continue writing this as P times alpha minus beta. We know what it is, so it is the diagonal matrix times P minus 1 times V. So here is the matrix A. A is P 1, 0, 0, minus 1 p minus 1. That is now the matrix that we are interested in. So you have probably seen an expression like this connected to the basis change, and now we see how this is derived. So we want to find the matrix A, and from our three steps, we see that it is actually a product of three matrices. P, the diagonal matrix, 1, 0, 0, minus 1. P is obtained by taking the new basis vectors as columns, times the inverse of the matrix P. Let us now proceed with our specific calculations. So once again, the matrix A is equal to P times the diagonal matrix times P inverse. To find P inverse, we use the following formula. So recall the formula for the inverse of A, B, C, D is equal to 1 divided by its determinant times the 2 by 2 matrix, where we swap the entries D and A, and we keep the entries B and C but change their signs. Applied to our matrix, 3 minus 2, 2, 3 inverse is equal to 1 divided by the determinant, which is 9 plus 4, 13, and then 3, 3, 2, minus 2. We can substitute this and calculate A equal to 3 minus 2, 2, 3 times the diagonal matrix times the inverse 3, 2, minus 2, 3, and of course 1/13. So 1/13. So that is equal to 1/13. Multiply the first two matrices, we get 3, 2, 2 minus 3, and then here 3, 2 minus 2, 3, and the matrix multiplication will give us 5, 12, 12 minus 5. It is easy to check that this is correct. We can simply multiply A by the vectors 3, 2, and by vector minus 2, 3. In the first case, I leave the calculation to you. You will see that this is 3, 2, and in the second case, you will see that this is 2 minus 3. Then we know that the matrix is right, because if we yield the correct values for the basis, it will also, by linearity, yield the correct values for the rest. Using the same method as above, for the general vector, we'll have the following formula. So the general formula, so reflection with respect to line spanned by the vector AB, different from 0, will be given, so is given by the matrix A, which is 1 divided by A squared plus B squared, and then we'll get the formula A squared minus B squared. It will be a symmetric matrix, 2AB, 2AB, and here B squared minus A squared. You can derive this formula by tracing the steps of our calculation using AB instead of the vector which we've had. So this is how you use the basis change matrix to derive the formula for the reflection with respect to a line in a plane, both in special case but also in the general case.